Welcome back. In previous lesson, we studied power series and learned how infinite series can represent functions within their intervals of convergence. Today, we take the next important step by learning about Taylor polynomials and how they can be used to approximate complicated functions with remarkable accuracy. Recall that if a function is infinitely differentiable at a point A, it can often be represented by its Taylor series. On the screen, we have the formal definition of the Taylor series. This formulation allows us to represent a smooth function as an infinite sum of polynomial terms centered around the point A. Notice that a Taylor series contains infinitely many terms. While this infinite representation is extremely useful in theory, in practical applications, we usually cannot work with infinitely many terms. Instead, we keep only the first terms of the series. This finite approximation leads to one of the most important ideas in calculus, the Taylor polynomial. Here is the general form of the n-degree Taylor polynomial. Notice how each successive term built upon the previous ones. Incorporating higher order derivatives evaluate at our center A. You can think of the Taylor polynomial as a simplified version of the function that's much easier to evaluate and manipulate. Near the center point A, the polynomial closely follows the behavior of the original function. In many cases, even a low-degree Taylor polynomial can provide an excellent approximation. Throughout this lesson, we will learn how to construct Taylor polynomials, use them to approximate functions, and most importantly, estimate the error introduced by these approximations. Let's begin with an example. Consider the exponential function e to the x. One reason this function is so important is that all of its derivatives are equal to itself. As shown, the Maclaurin series for e to the x takes a beautiful, predictable form. We simply add terms of increasing power of x divided by their corresponding factorials. From this infinite series, we can construct Taylor polynomials of different degrees. As you can see, the degree 1 polynomial gives us a simple linear approximation. Moving to degree 2, we add a quadratic term and for degree 3, a cube term. Each additional term captures more information about the function and generally improves the approximation. To approximate e raised to the power of 1/2, we substitute x equals 0.5 into our third degree polynomial. Evaluating and summing these individual terms gives us an approximate value of 1.6458. Now compare this with the actual calculator value. By taking the difference, we can find that our absolute error is extremely small, approximately 0.0029. This is a very small error. A polynomial containing only 4 terms already provides a highly accurate approximation. This example illustrates one of the central ideas of Taylor approximations. As the degree of the polynomial increases, the approximation becomes closer to the actual function. Of course, whenever we replace a function with a polynomial, some error is introduced. How can we measure that error? That question leads us to Taylor's theorem. In the previous example, we used a polynomial to approximate e to the power of 1/2. But how accurate was that approximation? Taylor's theorem answers this question. According to the Taylor's theorem, the exact function value equals our polynomial approximation plus a remainder term denoted as r sub n of x. Here, p sub n of x is the Taylor polynomial and r sub n of x is called the remainder terms or error term. The remainder represents the difference between the true value of the function and the value predicted by the Taylor polynomial. To estimate this error, we use the Lagrange error formula. Notice its structure. It closely resembles the next terms in the Taylor series, but the derivatives is evaluated at some unknown point c located between a and x. Also, we usually do not know the exact value of c. This formula provides a powerful way to estimate the size of the error. Notice that the error depends on the three important factors: the size of the next derivative, the distance from the center point, and the degree of the Taylor polynomial. Generally speaking, higher degree polynomials produce smaller errors. In practice, we often use an upper bound. This gives us the Taylor error bound formula. By finding a maximum value m for that next derivative, we establish a guaranteed upper limit on our approximation error. By using this formula, we can determine whether a Taylor polynomial is sufficiently accurate for a particular application. In fact, it helps answer one of the most practical questions in numerical analysis: how many terms are needed to achieve a desired level of accuracy? Let us see how this works in practice. Let us return to our approximation of e raised to the power 1/2 using third degree Taylor polynomial. Since every derivative of e to the x is again e to the x, we need an upper bound for the fourth derivative on the interval from 0 to 1/2. Because e to the x is increasing, its maximum value on this interval occurs at x equals 1/2. Therefore, we choose m equals e raised to the power 1/2, which is approximately 1.648721. Substituting our values into the error bound formula using our upper bound m, 4 factorial, and our distance from the center, we calculate a guaranteed maximum error of roughly 0.0043. Notice that our previously computed error of 0.0029 is indeed safely below this bound. Now suppose we want the approximation error to be less than 0.001. How do we know whether a particular Taylor polynomial is accurate enough? This is called a desired accuracy problem. We simply increase the degree of the Taylor polynomial until the error bound becomes smaller than the required tolerance. Let us examine another example. Consider the sinus function. Looking at the Maclaurin series of the sinus function, notice that it consists entirely to odd powers of x with alternating sign. Using just the degree 3 polynomial and substituting x equals 0.5, we evaluate the expression to get an approximation of roughly 0.4792. Comparing this to the true calculator value, we find an absolute error of just 0.00026. This is incredibly precise, especially considering we used only 2 non-zero terms. These examples demonstrate the remarkable power of Taylor polynomial. Near the center of expansion, the Taylor polynomial and the original function are often almost indistinguishable. As the degree increases, the approximation becomes more accurate and remain reliable over a large interval. Because of this property, Taylor approximations are used extensively in science, engineering, physics, machine learning, numerical analysis, and computer software. Many calculators and computer programs evaluate complicated functions by replacing them with carefully chosen polynomial approximations. Taylor polynomials provide a practical bridge between complicated functions and simple algebraic expression, allowing us to perform accurate computation while maintaining control over the approximation error. Thank you very much for watching this video. The story of calculus isn't finished yet. I will back in the next video with another important tutorial. In order not to miss it, definitely subscribe to the channel and ring the bell.